Hi folks, this is problem 6 on the practice exam. So in this problem, we have a pole that's fixed here with two strings tied to it. We have an upper one and a lower one. And they both make an angle theta with the horizontal. It's the same angle on both. And there is some object, it's a ball I think, over here. And this is spinning around. So this is going around like so. Get my perspective right someday. Do I give you the angular velocity here? Yes. So this is going round at an angular velocity omega. And there are several steps to the problem, but they're just kind of there to get you to find T1 and T2 in terms of the other things. So I think I called the upper one T1 and the lower one T2. So part A, draw the cartoon, draw a force diagram, and pick a coordinate system as part A. So, well, forces are pretty simple. We've got two strings and the weight of the thing. So, thing. Oops. We'll draw this a little bit bigger. Should always err on the side of making these big because we're going to need to do some trig. So we have the tension of the first one going that way, the tension of the second one, looking for the color of chalk that's in my hand, going that way, and we have gravity going down. Now we're going to need to do a bit of trig. So let's see, the angles we know are the angles with the horizontal. So those are the two angles we know. So that means that I'm just going to draw the components in purple. So this up here is T1 cosine theta. This one there is T1 sine theta. This one is T2 sine theta. And that one is going to be T2 cosine theta. We know in this problem that our acceleration vector is pointing inward. There's my acceleration vector. And when I choose a coordinate system, I want to line my coordinate system up with the acceleration vector whenever I can. When I pick my coordinate system, I'm going to do this. Because notice everything is going to the left here. So I'm going to choose my positive x direction to be the left. Can I do that? Absolutely. So there's that. Since I'm going in a circle, I know my acceleration vector has magnitude omega squared r toward the middle. Yes, Dinara, because I've used the same symbol for them in the problem, you can assume they're both equal. The problem says one is at an angle theta above the horizontal, the other one is at an angle theta below the horizontal. So yes, if I'd given you two different variables, they'd be different, but they're the same here. So start with force diagrams, then write down Newton's laws in x and y. So sum of the forces in the x direction equals max. Sum of the forces in the y direction equals may. Okay, so here we just read them off. In the x direction, all I've got are the horizontal components of the tensions. So T1 cosine theta plus T2 cosine theta equals m times the acceleration in the x direction. So max, but we know ax is omega squared r. And then in the y direction, let's see, I've got T1 sine theta going up, T2 sine theta, and mg going down. So I have T1 sine theta, but now the signs change, minus T2 sine theta minus mg. And here I'm just going to skip a step and write equals 0, because I know the acceleration in the y direction is 0. So you all had asked for a review of substitution shenanigans. Here I have two equations with two unknowns. I don't know T1 and I don't know T2. Simple enough. This problem, this is one where the algebra can get a little bit sticky. I may not have enough room over there to do it. But ultimately, it's the same approach. Solve for one variable, substitute it in, find the other one. I'm just going to pick one at random. So if here I solve for T1, I will get an expression for T1 that I can then substitute in here and find T2. So let's go ahead and get started. Let's see, I need blue and white. So this equation I need green as well. So this gives me T1 cosine theta. I put everything else on the other side. Equals m omega squared r minus T2 cosine theta. So that tells me that T1 equals m omega squared r minus T2 cosine theta, all divided by cosine theta. Or, you know what, I'm going to go ahead and split the fraction up. I think that would wind up being easier. So it's m omega squared r over cosine theta minus T2. So now I'm going to substitute that in there. So I take this equation and I bring it up here. And that's going to become, so I've got that thing times sine theta. So m omega squared r, we'll stick with colors. M omega squared r over cosine theta times sine theta minus T2 times sine theta. So that's all this. You know what? I need more room for this. So I'm going to wind up cramping myself on the board. So what I'm going to do is I'm just going to keep these two equations, erase everything else, and put it on the left. This is a problem where there is just a bit of algebra. So we're gonna do this again. Sorry about that, folks. So let's restart. So this equation we're going to solve for T1. So equation 1 gives us T1 equals T2 minus m omega squared r over cosine theta. So now we substitute that into number 2. So I'm going to write the part that I substituted in orange and the rest in blue. So that gives me T2 sine theta. Whoops. No, I made an error here. I was going too fast. The signs are reversed here. So here it should be the other way around. Got it right the first time. This is what happens when I go too fast when I'm hungry. So this is m omega squared r over cosine theta minus T2. So now we do the substitution. So now we plug in for this. So T1 becomes this formula. So this gives us m omega squared r over cosine theta times sine theta minus T2 times sine theta. So that's this piece. Now I have the whole rest of the equation. Minus T2 sine theta minus mg equals 0. So this looks kind of god-awful, right? But I can combine things, and I notice that sine theta divided by cosine theta is tangent. So this gives me m omega squared r tan theta minus mg equals 2 T2 sine theta. That's not so bad. I can now divide by 2 sine theta to get T2 equals m omega squared r tangent theta minus mg all over 2 sine theta. And then with this, I can substitute that back into number 1 or back into number 2 to find T1. So this is an example of double substitution where you're interested in both variables. So here we have found T2, but we also want T1. So I'm going to substitute into here. So let's see, I've got T1 sine theta minus T2 sine theta. So let's see, T2 sine theta, the sine theta cancels that one. So minus m omega squared r tangent theta minus mg all over 2 minus mg equals 0. Hey, this is an equation that's just got a T1 in it, right? So T1 equals all of this garbage divided by sine theta. And, I'm out of room. I'm not going to write it all down. But this is just an exercise in doing some algebra. If you didn't get the algebra, but you got the setup here, you would get almost all of the credit. I'm going quickly here because I am on limited time and I want to get to the other problems. Are there any questions about what we did here? Like, I've been waving my hands at algebra, but really getting to these two equations from Newton's laws that's all the physics. And after that, it's just an algebra game. So if you kind of zoned out during the algebra, totally fine. It's not important. All right, I'm going to pause the recording here.